Hello and welcome to the third in this short series of videos about noise. In this one we're going to be looking at the frequency content of noise. I should explain what I mean by that. You can take any noise signal and then if you pass that noise signal through a series of bandpass filters, each of which only allows through a small range of frequencies, and look at the output of those filters, then you will get at the output of those filters a different range of frequencies in the noise, a different noise signal. Those noise signals sound different, but if you added them up, you would get the original noise signal. Looking at how much noise appears in the output of each of those bandpass filters, that gives you information about how much of the power in the noise is in each of those frequency ranges. And that's what we mean by noise spectral density. And now compare that to this noise. They sound different because they have different amounts of energy at different frequencies within that noise signal. You can divide up any noise waveform into a lot of different frequency bands and just look at what noise exists in the frequencies in that frequency band. For example, if I take this noise here, that's the noise between 0 Hertz and 100 Hertz, and add this noise, that's the noise between 100 and 200 Hertz, and this noise here, that's the noise between 200 and 300 Hertz. If I take those three noises and add them together, then the result sounds like this. The total noise between 0 and 300 Hertz. If I then add this noise, the noise between 300 and 1 kilohertz, I end up with this signal here, which is the noise between 0 and 1 kilohertz. Add the noise between 1 kilohertz and 2 kilohertz, and we get the final noise between 0 and 2 kilohertz. If I then add the noise between 2 kilohertz and 20 kilohertz, which sounds like this, I end up with all of the noise in the human audio hearing range. And that sounds like this. You can plot the amount of noise power in all of these different frequency bands on a graph. And that graph is known as a power spectral density graph. You do it by first dividing the frequencies into a number of ranges between typically 0 and 22.05 kilohertz, because that is half of the standard CD audio sampling rate of 44.1 kilohertz, and therefore it's the maximum frequency that can be analysed by any system sampling at 44.1 kilohertz. Once we've divided our frequencies into these ranges, we then apply a series of filters just to pick out how much noise is in each one of those frequency ranges, estimate the amount of energy in each range, and plot the result in a histogram. Audacity is very good at doing this and can plot these graphs. These are a couple of graphs output from Audacity with two different types of noise being analysed. This one, you'll notice that almost all of the frequency ranges, and there are currently 512 frequency ranges, that's what the size parameter does, almost all of them have a power of about minus 26 dB. In fact, they're all within plus or minus 0.3 dB of minus 26 dB. This is a type of noise that we tend to call white noise. there's approximately an equal amount of power in any one of these frequency ranges. Whereas this noise here is definitely not white. We have quite a lot more power in these range of frequencies here, around about 5 kilohertz, and a lot less power at higher frequencies and at lower frequencies. We also have these spikes here, where we have a lot of noise energy at specific frequencies, multiples of 1 kilohertz. Talk a bit more about that plot later. So far, I've just been talking about audio frequencies. There's a rather interesting effect when you consider not just the audio frequencies, but every possible frequency of noise. There are, in theory, an infinite number of frequencies. If we have white noise, with a certain amount of power in each small frequency band, well, if there are an infinite number of frequency bands, then there must be an infinite power of noise. Yes. This is one of the observations that led to the development of quantum theory and quantum mechanics in physics. As electronic engineers, certainly just beginning electronic engineers, we don't have to worry about this because it only becomes a problem for frequencies up in the terahertz range, which is not going to be a problem for us yet. What is more of an issue is if we're dealing with signals which are not audio signals, but which have a different bandwidth. In these cases, we often don't know the bandwidth of interest to the final system designer when we're trying to specify and analyze the noise. So we cannot work out the total amount of noise that's likely to be in the system that the designer is interested in. What we can do is specify how much noise there is per unit bandwidth. And then a designer can just take that value, combine it with the knowledge of the bandwidth that they're interested in, and determine the final noise bandwidth in all of the frequencies that they are concerned with. Finally, for this video, I'd like to introduce you to the potentially rather strange looking unit of volts per root hertz. We often specify the amount of noise that a system or a component introduces in terms of volts per root hertz. Why volts per root hertz and not volts per hertz? Well, the reason is because when we combine different noise sources, for example, the noise in 1 hertz of bandwidth and the noise in a different hertz of bandwidth, we have to add the powers rather than the amplitudes. I'll come on to why we have to add power rather than amplitude in future videos. For now, please just accept that that's what we have to do. Okay then, so supposing that the noise voltage in a 1 hertz bandwidth was X volts RMS. That would mean that the noise power in that 1 hertz bandwidth was X squared. So, if we can assume that there is the same amount of noise in all 1 hertz bandwidths, which is another way of saying the noise is white, again, more about that later, if we can assume this, then we could say that the noise in 2 hertz bandwidths, bear in mind that we have to add powers, not voltages, would have a power of 2x squared. The voltage is the square root of the power, so that would be square root of 2 times x v RMS. And if we had a bandwidth of b hertz with the same power in all of the 1 hertz bandwidths within b hertz, that would have a total power of bx squared, and therefore a total RMS voltage of the square root of b times x v RMS. That would be our noise voltage. Now, square root of b times x has units of v RMS. The square root of b is the square root of a bandwidth. Therefore, the square root of b has units of the square root of Hertz. So x must have units of VRMS per root Hertz, so that when we take x and we multiply it by the square root of the bandwidth, which has units of Hertz, we end up with something which has units of x times the square root of b, units of VRMS. I'll put the units in brackets. So x, the noise voltage in 1 Hertz of bandwidth, actually has units of VRMS per root Hertz. This allows us to calculate the amount of noise in any bandwidth b just by taking x in VRMS per root Hertz, multiplying it by the square root of the bandwidth, getting x square root of b, and that's the amount of noise voltage, the RMS noise voltage, I would get in a bandwidth of b. But it's important to note that this only works if the noise has a constant value of VRMS per root Hertz across all of the frequencies in the bandwidth b. If it doesn't, then we can't do a simple multiplication like that. What we can do, however, is instead of just a simple multiplication, we can use an integration to add up the contributions of each of the tiny little frequency ranges within the bandwidth b. So instead of doing a multiplication, we have to do an integration of the power spectral density. The power spectral density is a function of frequency, and it tells me how much power there is in 1 Hertz of bandwidth. So in other words, in terms of what we've used before, it was just x squared. The power in a unit of bandwidth. And if I integrate that over my frequency range of interest, let's say I'm interested in frequencies from f0 to f1, that would be the total noise power that I would expect in my system. And I can express that in terms of the total noise voltage, if I wanted that, just by noting that the power spectral density is the square of the noise voltage in RMS per root Hertz. But now we're assuming that the noise voltage in RMS per root Hertz is a function of frequency. We can get it from the power spectral density, since the power spectral density, the amount of power in 1 Hertz bandwidth, is just the square of the noise voltage spectral density. So I would take the noise voltage spectral density, square it to get this. This gives me my total noise power. If I took the square root of my total noise power, I would get the total noise voltage, the total RMS noise voltage. I'd have to write something like this. It's beginning to look a little bit unwieldy, and this is one of the reasons why people often prefer to talk about powers in noise rather than voltages. That's all I wanted to say this time. Next time we'll have a look at colours of noise.